and to moderate this next talk, I'm delighted to introduce Roxana Rata. Roxana is a radiation protection physicist and with a real interest in accelerator applications in the medical field. She did her PhD in radiation protection for proton therapy, and after that, she joined CERN as a senior fellow. After CERN, Roxana worked as a radiation protection specialist for the British government. 1 year ago, she joined Varian Medical System as a beam physics engineer for the proton therapy systems there. Roxana, the floor is yours.
Thank you so much. I am delighted to be here today. Thank you so much, Anelia, for the introduction. And I guess that now it is my turn to introduce the new guest. His name is Markus Hager, and Markus has experience of more than 10 years in healthcare. He started with commissioning one of the treatment facility, and after that he joined MedAustron team at CERN, where he developed a new software that generates the accelerator setup for the large beam in use for cancer treatments. So to understand more on radiation therapy, he continued his studies doing a master in radiation therapy. And now he's working at Cosylab, where he's helping other clients to develop innovative treatments. So Markus, the floor is yours.
Oh, Roxana, thank you for this nice introduction. Yeah, you mentioned some of the aspects that I'll talk about. Also the work at CERN, which I'll explain in a bit more detail. It is correct. I used to work on the accelerator side with the accelerator control system, on controlling really all the different elements of an accelerator to get them to work together and produce a decent beam. Often enough, that is not easy, right? We had days where we were really struggling to get a nice beam out of the accelerator. And so I kept asking myself, how is this beam then used, right? Proton particle therapy is one of the most advanced therapy forms for cancer that is available today. So how does that all work? And yeah, so I decided to go back to university to find out more about this. And yeah, for today, I thought when I worked at CERN, I was really curious about how beams are used for medical treatments. Today I know more about it, so I'll share this knowledge, hoping that you find it interesting as well. And so in my talk today, I will take you from the world of accelerators into the world of cancer treatments. That is the idea. But let me start with the accelerator side. And on this slide here, I have a picture of the MedAustron accelerator. So MedAustron is a treatment facility in Austria. They are treating patients with protons and since some time also with carbon ions. And the MedAustron accelerator was built in cooperation with CERN. So some years ago already, CERN developed a study investigating, how synchrotrons could be used medically. And then MedAustron, when the decision for this accelerator was taken, they agreed with CERN to work together to collaborate on building the actual synchrotron. And so a large number of MedAustron employees spent time at CERN. I, in particular, worked in the accelerator controls group. So I worked with Johannes Gutleber from CERN, some of you might know. And so the MedAustron machine is a synchrotron machine that we built, and I mentioned it can produce proton and carbon beams. Those are the most typical beams that are used for cancer therapy today. if you look at the machine with the CERN knowledge in the back, it's maybe not that interesting a machine, right? It's 78 meters circumference. It can produce protons with up to 800 MeV. So compared to CERN accelerator, not that much. For clinical use, even these 800 MeVs are way too much. 250 MeVs are enough. So from that perspective, perhaps medical synchrotron is not that interesting, but there are some factors that make it a challenge to use synchrotrons medically, and I'll explain how come. The first thing that I need to explain is how the beam of the synchrotron is actually used in a medical treatment, and I have this on the slide here. So the beam from the accelerator is this green line in the picture. It's delivered to the patient and to the tumor volume. We call it typically a pencil beam. It has a size of about 5 millimeters typically. And now particles have a very special, very distinct way of interacting with matter. So particles that travel through tissue, they will deliver some energy, they will slow down gradually, and then shortly before they come to a stop, they deliver all of the remaining energy in a very, very short distance. And this distance, distance is here in the diagram. It's this peak. The peak is called the Bragg peak. And this peak is what makes particles interesting for treatments. The peaks allows to focus the energy delivery of the beams to a specific region. The area to where the energy is delivered, this peak depends on the initial energy of the beam. So the higher the energy of the particles, the deeper in tissue or in matter really this peak will be produced. And in a treatment, the energies of the beams are chosen such that they put this peak into the tumor, and that then means that the dose is delivered to the tumor, but after the tumor there's really not much energy, or in fact no energy at all that is delivered. And that of course helps to focus the energy of the tumor, of the energy of the beam to the tumor, and spare the tissue that surrounds the tumor. Right, that brings me back to deliver energy to a bigger region, to the target region. It's not enough to use only one beam with one energy, but beams with multiple energies need to be used to stack the beam. Right, the Bragg peaks are thin. The pencil beams are not that thick, so to cover a bigger area, the beams are scanned, different beam energies are used. And that, in fact, is one of the challenges of a medical synchrotron. So the synchrotron does not only need to be set up to provide one energy, it needs to be set up to provide many energies. For the clinical use, I have the examples here, 60 to 200 MeV. The spacing between two slices is perhaps half of MeV or 1 MeV. And so now all of the elements of the accelerator, they need to know what to do to deliver a beam of a certain energy. So MedAustron accelerator has several hundred magnets, different RF structures. The timing needs to be right. And all of this needs to be calculated for the different particle types, for the different energies, the different beam sizes, even the intensity of the extraction. And so what I did at CERN, I worked with our accelerator physicists, and I developed the software that does these calculations. So in that software, the physicists would enter, for example, the tune or the chromaticity of the synchrotron, and the software would then in the back use MedX, would do some optics calculations, and would produce the waveforms and the set points for the different magnets and elements of the accelerator, would produce the timing sequences. So this worked very well. Here are the results. It's really a measurement of the beams at MedAustron. MedAustron started treating patients in 2016. So the software that I developed, the cycle configurator, obviously worked nicely. It helped to set up the accelerator to treat patients. I think by today, MedAustron treated several hundred patients. And it's, of course, not only a success story for the work I did, but I think a success story for CERN in general, right? For the knowledge transfer of CERN and the positive impact that CERN and studies like the PIMS study that investigated the use of medical accelerators and that was produced at CERN, that they really have a positive impact on society. Now, what I promised you is that I take you from the accelerator side to the medical side. And to do that, I first need to explain how particle beams produce some treatment effect, right, a medical effect. And the starting point of that are ionizing events. So what happens is that particles interact with electrons mostly. For example, they can kick an electron out of its place, causing an atom to become an ion. But electrons are used in the bonds between atoms, in the bonds between molecules, and molecules forming important structures in the body. The DNA of a cell, for example, which I have here on the figure. And the energy transfer of the beam now causing these ionizing events can mean that these bonds are messed up, that the bonds between important structures in the body are broken, which can mean, in case of the DNA, that there is damage caused to the DNA. Now, cells can repair DNA. Of course, this is important, otherwise we wouldn't live. But if enough of this damage is caused, then cells cannot repair it anymore and they die. And if it's the tumor cells that are damaged and die, then we have the tumor treated. Of course, this is not the entire story. Yeah, the ionizing events are a starting point, but the way that cells really react to these events, they depend on a lot of different factors. They, for example, depend on the particle type. They depend on the type of the cell, right, on the type of the tissue. They even depend on the amount of oxygen that is available in cells. And then also cells don't live alone. Cells live in big structures. They form organs, right? They communicate with each other. And they also communicate with the immune system, meaning that also the immune system starts to interfere with the reaction of the body on the radiation that is delivered. The reaction of the immune system is something that we only starting today, I think, to really understand. And all of this together in the end, all these factors together in the end, then cause a biological response, which means, well, that the tumor dies and that the patient can live without the tumor. In the medical community, this is called a disease-free survival. But the lifespan, of course, is not the only aspect. It's also a question of how good is the life, how much side effects does a patient have. And this knowledge really of how radiation affects the body as such and the biological response it causes, that is now knowledge that oncologists have, right? That is the knowledge of medical doctors. And for a treatment, the medical doctors bring their knowledge in, they diagnose the patient, and they define the type of treatment, they define the particle type to be used, they define the doses to be delivered, the amount of radiation. And they would also define the target volume, of course, right? The part of the body that needs to be treated. In my example here on the slide, this is a CT scan, and it shows the prostate in the middle in red, which in my examples will be the target volume, that it's a prostate treatment. So oncologists would use a special software treatment planning system and would in this software actually draw the volumes that are interesting. They would draw the target volume, but they would also draw structures that should not be irradiated. The rectum, for example, which is the brown part, is down here. The rectum is very sensitive to radiation. If the rectum was irradiated, it might give a patient severe side effects in going to the toilet, problems with that. And that is, of course, something that we don't want to have in as an outcome of a treatment. And so what happens in treatment planning is that these aspects are considered, that oncologists prescribe the targets, and also marked the volumes, that targets that should not get those. And then the right setup of the treatment is determined. I have two examples here. I have one where it's 4 beams coming, 2 from the sides, 1 from the front, 1 from the back, compared to one that only has 2 lateral beams here in the center. And so the question, in both options are feasible, really. The question is, which one is the more suited for a treatment? That's what's determined in treatment planning. And I can tell you the more suited is the case with the 2 lateral beams. The reason being that, again, we want to avoid those being delivered to the rectum. So a beam that comes from the back, for example, would exactly deliver those to that structure and should be avoided. Whereas from the sides, the beams go through the bones here. This is the femoral head. And the bones in adults are not very sensitive to radiation. They can take a lot of radiation without side effects that occur. So the better setup in this case is with 2 beams from the side. That is what is defined in the treatment planning system. The treatment planning system then calculates the dose, and it calculates which energies and which beams it needs from the accelerator. And that brings me back to the accelerator side. So I have here the accelerator of a facility in Germany, Heidelberg, Ion Beam Therapy Center. And what I think this slide really nicely shows are the dimensions of this treatment, really. The synchrotron being a complex, bigger machine compared to the patient. The beam is accelerated, is then delivered to the patient, as I've shown on previous slides. But then the particles, when they leave the accelerator, they go their path, right? They basically go straight. And so what we still need to do is we need to get the patient to where the beam is, get the tumor really into the path of the beam. And this is the last part that I want to show you in my talk now, how the patients are set up. So patients are positioned on a robotic system. Yes, a robotic arm. Again, these are examples from MedAustron. Patients are positioned on the treatment couch. Typically, there are these, for head and neck treatments, typically these face masks are used. So they are a plastic mesh that is heated in warm water. When it's warm, it becomes soft, and it can then be pulled down over the patient's face. It's mounted in a certain position on the treatment couch. And then it gets cold and it remains in this form. And then every time the patient comes for the radiation, this mask is placed over their head and mounted on the table again. And that ensures that the patient is really lying in the correct position on the couch. There are some other options. You could use a vacuum mattress. So it's a foam mattress, and air is sucked out. And then it keeps the form of the patient. It's another device. Or down here is a knee rest, also a device that can help to position the patient in the right position for the treatment. You might still ask me, Markus, this all looks like it's not very accurate. How can you, accurately treat the patient? And I'll show you the answer to that. In fact, all aspects of a treatment have uncertainties. That's important to know. It starts with the prescription of the oncologist, right? Different oncologists would draw tumor volumes that are a bit different. It also includes physical aspects, like the proton range, for example. It's not clear where in the body protons will stop. There's certain inaccuracy. And then it's the setting up the patient on the robotic couch, immobilizing the patients. All of this has some uncertainties that need to be addressed. And well, the way to do that really is to consider it in treatment planning already. And in fact, the way out is to irradiate a structure that is bigger than the actual target volume. So in the treatment planning, bigger volumes are designed that include additional margins to account for those uncertainties. So in the end, we'll deliver a bit more radiation to a bigger volume than strictly necessary, but that helps us to ensure that we really cover the tumor volume with the required dose, even if there are some uncertainties in the treatment. So with this, I think we started talking about the accelerator setup, the different energies. I explained a bit about the delivery of the beam. We looked at how patients can be set up. I explained the medical aspects with ionizing events and the biological reaction, how this is used in treatment planning. And so in the end, the setup of the accelerator determines the biological response. And we looked at this entire chain of how particle beams are really used to treat cancer. It was only a short overview. There's, of course, a lot more we could talk about. I hope you still found it interesting. You have some opportunity to ask me more. I will be in this networking session at 4:30. You can also find me on LinkedIn or on the alumni portal. I put also the link here of this master program that I did. It's a program taught in English. It's in Austria, but it's taught in English. It's a part-time study. So if you're interested in radiation therapy and in learning more about it, perhaps this program is something that is of interest to you. Also, today I'm working at Cosylab, which is a really interesting company. We are very much involved in particle therapy and in new ways of using it, very innovative solutions. There's a lot of open positions. If you have any interest in the software domain and working at Cosylab, check out those positions. If you'd be interested in working with Cosylab on some particle therapy related field, I'd also be happy to hear from you. You can contact me at my Cosylab address, which I put on the slides here as well. And that is really the end of my talk. Thank you for listening.
Oh, thank you so much, Markus, for this very well done presentation, very precise and very good information on it. So we have now 10 minutes for questions. So feel free to write your questions on the chat if you have one. Yeah, meanwhile, I have some questions for you, Markus, if that's all right with you.
Sure, great, Roxana.
So I'm not aware of MedAustron, but do they have a research room?
They do have a research
That's
room
why,
as well, yeah.
Yeah. Okay, and
That's why I
that's the
mentioned
maximum energy used.
That's the maximum energy
Okay.
used. Those are these 800 MeVs. Yeah, for a treatment, it's way too much energy. It would put these Bragg peaks outside of the body, but that's not what one is interested in, right? We want to have the Bragg peak in the body, in the tumor volume, really. And for that 250 MeV, they can deliver beams already to some 25, 28 centimeters depth in water, and that is really enough for treatments.
Yeah. Do they use carbons as well, or?
They do since, I think, 2019. They also have carbon ions set up, and they are using them for treatments.
Okay, I was not aware of that. So it's something that came 2 years ago, let's say.
Yeah.
Okay. In your opinion, what are the things that could be improved in particle therapy?
Yeah, there are some aspects. The one is that it's still a bit more expensive than other forms of therapy. So one big goal would be to make the treatments cheaper, which would mean that the accelerators, for example, should become cheaper, smaller, simpler than this complex synchrotrons used at MedAustron. That is one aspect. Another aspect is that this biological response is still not understood too well. So there is a lot of research going on in that area, the reaction of the cells and the reaction of the entire body and the immune system to radiation. There's a lot of research going on in that area. and some new findings coming out, examples, flash therapy or microbeams that can, with even less irradiation, reach very good treatment outcomes. So it's ways to spare even more healthy structure to deliver less dose and still reach even better treatment outcomes. These are things that are investigated at the moment and that I think will be important in the future of particle therapy.
Yeah, I see. What things do you think that scare people most when they are having treatments with protons, for example? I mean, the side effects. Uh, in your opinion, the side effects are something to be scared of? Because many people, they are asking me, for example, oh, if I am irradiated, what will happen after? So do you think that people should be scared about the side effects after proton therapy?
No, I think there is no reason to. This is the main advantage of proton therapy, that the side effects are very, very limited. Very typical side effect would be that the skin gets gets infected because there's always some energy delivered superficially as well. But these are minor side effects. Otherwise, I think exactly proton therapy has a very good sparing of healthy tissue. In treatment planning, they really make sure that the critical structures are spared. Right, I showed this example of the rectum. So they check some dose will be delivered to the rectum as well. That can't be avoided, also because of the margins that are necessary to account for the uncertainties. But in treatment planning, they ensure that this is only so much dose that the rectum can tolerate, and then it's overall over the entire treatment. It's not, it won't have bigger consequences for the patients.
Okay, thank you so much for your explanation. It seems that we don't have questions.
If you have a few more
So,
minutes, there are some interesting aspects going on. Also, CERN is still very actively involved in this community. I can mention that. So they did this PIMS study for this accelerator that the MedAustron accelerator is based on. Today they have a study called NIMS, New Ion Medical Machine Study. That study is in particular investigating the production of carbon ion beams and what are the best accelerator techniques to do that for treatments. Other examples are this flash therapy that I mentioned. CERN is involved in that with, I think, a university in France. So flash therapy delivers very high doses in a very short time. Something that also CERN is involved in with the accelerator technologies. There's also some spin-offs, like companies like AVO, Atom, that are working on producing accelerators that are smaller. They're using a LINAC that is very small in its footprint. And it's a spin-off of CERN, so it's also technology developed together with CERN. So CERN is still very active in this field, and I think there's a lot going on in terms of particle therapy today. Still, it's a very interesting field, really.
we have some questions in the chat. So the first one is: it is necessary to build a new building or even a new hospital to place the accelerator?
Yeah, not necessarily. A big machine like the synchrotron from MedAustron needs an entire building. But what I just mentioned, AVO, for example, with this LINAC, they are planning to install this LINAC in existing buildings. And it's not only AVO, there's other companies, Proton, for example, as well, that build very small accelerators that can be installed in existing treatment facilities, even in existing treatment rooms.
I see. The next question is: which is the average hadron therapy treatment duration?
I'd say something like 20 fractions. The radiation is fractionated, so the patient has to come 20 times. Usually this is done on the work days, so 5 times a week over 4 weeks. That's a typical course for a treatment.
I have another interesting question. Is an online monitoring of the deposited dose feasible? Could it help reduce the side effects by adjusting the near real time the patient position?
Interesting question. Yeah, there are some ideas to do that. It's not trivial, but there are, especially with carbon ion beams, there are some PET nucleate PET radiation that is produced and that could be measured in real time. There are other ideas to measure the dose. There's, for example, proton imaging, where the proton beam is really used not only for treatment but for imaging as well, and that could really help to figure out where in the body the dose is delivered. There's a lot of research going on in this area really to find good solutions.
I see. Yeah, this is all. Yeah. Thank you so much, Markus. Thank you so
Thank
much
you.
for your presentation.
Goodbye.